What's up, guys? My name is Rachel Thornton. I'm recording a short video on topology for the Directed Reading Program Spring 2020. Quick shout out to Michael Starbird and Francis Sue, who wrote the book that I'm pulling a problem from. If anyone has it, it's problem 2.14. We're going to be talking about a really important theorem in topology today, but this video is meant to be digestible for anyone who just has a strong math background. So it's not just for topologists. So we need to start with the basics and talk about what is a topology. Let's jump right in. So, definition. Let X be a set, then T, which is a collection of subsets of X, is a topology on X if the following conditions are met. So first, we know that the empty set must be in our topology. We have the entire set of X is in our topology. If we have two sets, U and V, in our topology, then their intersection is also in our topology. And if we have a collection of sets in our topology, then the union of all of these sets is also in our topology. So that might be really, really hard to look at, so we're going to understand it with some examples. So we're going to start with the indiscrete topology. The indiscrete topology works on every single set. It is the most basic form of a topology, so you guys are going to like this. So, X is some set. The indiscrete topology is exactly this. The empty set and all of X. So let's go through the conditions that we needed to meet. The empty set is in our topology. Woohoo! We have X in our topology. If we have two sets in our topology, we only have two to pick from, then their intersection is in the topology. So the intersection of the empty set and the set of X is the empty set, which is in our topology. And the last condition is if we have a collection of sets in the topology, then their union must be in the topology. So the union of our only two sets is going to end up being X, which is in our topology. So the indiscrete topology works on all sets, so that's why I kept it very general. But for the next example, we're going to look at the standard topology on the real number line. So we're going to look at this now. So a set is in our topology if for every point in that set you can draw an open interval around the point. So let's draw it like this. We have 0, and let's say we have A and B. So we want to know if A, B is in our interval, then what we need to do is check that for every point in here we can draw an open interval around that point and have that open interval be completely contained inside this set. So for an open interval around here, A isn't in this set and B isn't in this set, so we just have to test other points. So to give you an idea, that's some random point in this set. We can draw an interval around it. The interval is contained in that set. To put it more formally, if C is actually in here, then what you can do is draw the interval C minus A over 2 to B minus C over 2. We're assuming that B is strictly larger than A. And then C is also going to be inside this interval, which is contained in that interval. So other examples of sets that are in this topology, you could have a set like this. So each of these, we understand that those are both in our topology, but when we union them, they're still in the topology because for all these points we can still draw the open interval around the point that's contained in the set. And that makes sense because that was part of our definition of a topology. And for an example that's not here, A and B. So this set is not in our topology because if we draw an open set around A, or an open interval around A, then we're always going to have part of that interval not be contained in this set. So to make that more clear, we have A, we have B. Here's the closed interval around that. So any open interval containing A is going to have a spill out outside of the set. So this set is not on a topology, but this set is, that set is, etc. So we got to move on to our next definition, which is an open set. So an open set means that, or if U, which is contained in X, is an open set, then that just means that U is in the topology. So in the examples we just did, AB was an open set. The union between AB and CD is an open set, but the closed interval from A to B is not an open set. So that's what an open set is. We got to move on to our next definition. So we're going to look at limit points. So let A be some point in X, then A is a limit point of the set A if for all open sets which contain little a, we have the intersection between the open set excluding little a and big A has to be non-empty. So to take it back to the real number line example, we have A and we have B. We know that all of the, we're looking at this set, so this is what we're calling our big A. And we want to know if little a is a limit point of this set. Then we need to verify that all open sets which contain A have non-zero overlap with this interval. So we know that all the open sets in the topology look like some kind of open interval like this, maybe union, maybe not, but if they contain A, then you'll see an open interval around A, which has non-empty overlap with the interval from A to B. That means that A is a limit point of AB. For the same reason, B is a limit point of AB, and also all of the points in here, like this random point C, is going to also be a limit point of the interval because, there's non-zero overlap. So that's what a limit point is, and that introduces our next idea, which is about closures. So, the closure of A is denoted with A bar, and it is the set of A together with all of the limit points of A. So in the example that we just did, if we have the closure of A, B, we know that A is a limit point of the interval from A to B, B is a limit point of A and B. Nothing outside of the interval was a limit point. So let's look real quick. I have some point just outside the interval. We can always make a small enough interval so that it has no overlap with this interval A to B. So only A, B, and all the points in between are limit points. So if you add them together or you union them, then you get this set. So the closure of the open interval from A to B is the closed interval from A to B. The closure of A, B is actually still the closed interval from A to B. So for the exact same reasoning as we did for the open interval, A and B are limit points. All the points inside this interval are limit points, but none of the points outside of it are limit points. So when we have a set like this, where the closure of the set is the set itself, then we say A is closed. So here is where it gets confusing. We've introduced the idea of open sets and we've introduced the idea of closed sets. What you need to understand before we jump into the theorem is that not being closed does not mean open. In topology, it was very poorly named, but you can have sets that are both closed and open, and you can have sets that are neither closed nor open. So let's go back to our indiscrete topology. I'm going to claim that X, which is in the topology, is both closed and open. So X, of course, is in the topology because it was just the empty set in all of X. So X is open, and any limit point of X has to be inside of X. So X contains all of its limit points. So the closure of X does not add any new points. So that means X is closed. When you have a set like this, we call X clopen. You can just enjoy that for a second. That's a really good time. So, we're going to move on to the theorem that we're creating this video for. It's a good time. So, consider the topology, this one. We have a subset of X, which is closed. Then we know that it's closed if and only if its complement is open. This theorem is foundational because even though we can't say that the opposite of closed is open in a topology, we can say that if a set is closed, then its complement is open. It relates closed and open in a really, really great way because they weren't related before this theorem. It's going to be used a lot in later topology. So if you can understand this theorem, you're going to understand a lot of topology proofs. So we got to do the first direction. So we need to show, we know that A is closed, and we need to show a complement is open. So the way that we're going to show that a complement is open is by showing that for all points in a complement, we have an open set such that C is in the open set, and then we're going to union all of these points in the complement, and we're going to end up getting a complement. And from our definition of a topology, we know that the union of all of these open sets is also going to be in our topology. But I'm getting ahead of myself. Let's slow down. So we know that A is closed. Let's draw a little bit of a picture. If A is closed, then it contains all of its limit points. That is equivalent to saying that all the points outside of A cannot be a limit point. So let C not be in A, or in other words, C is in a complement. Then C is not a limit point of A. So, from the definition of a limit point, just move that up. Oh my goodness, I'm writing sideways. Okay, so we know that C is not a limit point of A, which means that from our definition there exists an open set such that the open set, excluding the one point that wasn't in A, intersection with A, is in fact the empty set. Because if this wasn't true, then C would be a limit point of A, and since C is not in A, that would make A not closed. So we know that this set exists. Since its intersection with A is non-zero, and we're excluding C, but C is also inside of A complement, then we know that U is a subset of A complement. So now we can get to the really, really awesome part. So what we're going to do is take, we're going to find, for all the points in A complement, we're going to find the corresponding, or a corresponding open set which contains that point, and we're going to put it in this set. So for C in A complement. Then what we're going to do is union all of these open sets, which are all subsets of A complement, and that's going to end up being A complement itself. So from the definition of a topology, we know that this set is in our topology, and we know that it's a complement because it has, like, every point in a complement is in one of these open sets, and because none of these open sets contain any points that are not in a complement. So we know that this means that a complement is in the topology. So a complement is open. All right, and the last thing that we need to do is go the other direction. This was an if and only if statement, which means that we need to prove it the other way. So just to refresh your memory, we had said if A is closed, or A is closed if and only if a complement is open. So now we need to assume a complement is open and show that A is closed. So A would be closed if all the limit points of A are in A. So if a limit point of A is in A. Yeah, okay. So this statement is equivalent to saying that all points not in A cannot be limit points of A. So if A is closed, if it contains all its limit points, then we need to show that all the points that are not in A cannot be limit points. Because that means if A has a limit point, then it must actually be in A, which would make A closed. So but we're going to show the second statement because it's a lot easier for this part of the proof. So all the points not in A are just points in A complement. And we need to show that they are not limit points of A. Well, we know that C is not a limit point of A if we can find an open set which contains C such that this is true. And we happen to know an open set that does just this. We know that A complement is open. So take U to be equal to A complement. Then we know that C, which is just some point that's not in A, must then be in A complement, and the intersection between A complement excluding C and A is, in fact, 0. Okay, sorry, yeah, we needed to show that this is 0. Okay, so what we just did was show that all the points that are not in A cannot be limit points of A, which means that A, if it has any limit points, those limit points must actually be in A. So A is equal to its closure. So A is closed. All right, cool, guys. So we just went in both directions, and it was a really fun time. So this theorem was really great because it related closed and open sets in a way that we didn't have before. We were still confused on whether or not open is the opposite of closed in topology, which it's not, which it just made it so much harder. But now that we have this theorem, we actually have a way to relate closed and open sets. And this theorem gets used a lot in topology, so if you understand this one, that's really great. I got nothing else to add. Okay, thanks. Bye.